LVDT is an abbreviation for linear variable differential transformer, and the principle is that you have a transformer inside a housing, and you have a slide here with a magnetic or a core for the transformer, and the core makes the transformer more efficient. So a bit more of how it works. Transformers are basically two coils close to each other, where you have a primary side and a secondary side. And the primary side is where you connect a power source, and the secondary side is where you connect a load. The idea is that the number of turns here and the efficiency of the transformer decides the relation of the voltage on the primary side compared to the voltage on the secondary side. So the voltage here is dependent on the number of turns related between the two, and how efficient the connection, the magnetic coupling of the two, how efficient that is. In an LVDT, you have a primary side which is connected to a source, and you have two secondary sides. And the two secondary sides are connected like this. Like that. Bit special. And then you have your core. Let's say that the core is in the middle here. What will happen is that the primary side, let's say that the current goes in this direction in the beginning for the primary side. Let's say that that generates a current on the secondary side which is equal for the two coils here, because the core is influencing on both coils equally much. So the influence here is equal for the two coils 1 and 2. So therefore the two currents that are generated on the secondary side are equal. Well, it looks like this current here goes down this line, and this current goes up this line, and the two meet. So they will actually cancel out each other. Now what happens if you have a core that is somewhere else, that is not in the middle between the two? Let's remove all the arrows here, and let's shift the core here over there. Still, let's have the primary current like this. Now this becomes more efficient, and I will symbolize that by having a thicker arrow and a thin arrow here, because this is not very efficient. So this now will create a thin, weak current, and this will create a thick, strong current. So there will be a net flow of current going in this direction here, giving a voltage plus minus here in the load. Okay, that was for that half of the signal voltage. Of course, the signal voltage will turn, the next moment it will turn the other way around, and you will get the plus minus like this. Now let's remove the arrows again. Let's keep the green and red plus and minus signs, just to remember how it was when the core was at the top side. Now let's draw a core that is here. I'm just keeping the black one for the moment where it used to be, but now it's downstairs. So now this one becomes most efficient, and this one is rather weak. The weak current goes there, the strong current goes up here. The two meet, and this one is the winner. So therefore you will have a strong current running in this direction. Now this will introduce a plus minus like this, and when the current here turns the other way, it will be a minus plus. So when the core shifts from this position to the mid position to the lower position here, you will have actually a strong current here, no current, and then a strong current in the other direction. And if it goes even further, you will actually have that the core has been removed totally. You will be back to zero current. So if we take a graph of position and current, let's like that. The current will be 0 when you're far away, then it will be strong, then it will go through 0 again, negative, and then back to 0. So here the core is out of range, in the middle, on the top coil, at the lower coil, and the useful region is actually between these two tops here. Here is the useful region between the two, because if you move it outside here, you can't distinguish this position from that position. So therefore, there is usually a mechanical element that will stop the core from going outside. So the core is now limited to shifting from here to here, which is within this area here. Let's draw it with black, from here to here, and the relation here is actually quite linear between the two. So therefore it's called a linear variable differential transformer. Going back to the PowerPoint again, these kind of sensors are very robust. They are very linear, they are more or less frictionless. The lifetime of such sensors is very large. They can withstand very high temperatures, very harsh environments, and vibrations and shock levels. They have low hysteresis, and they have excellent repeatability. So they are actually very popular in the industry for detecting a position for such a rod like this. Especially the long lifetime will be very useful in many applications.